materials stuff. So just a lot of sort of qualitative things to go with for each one of the particular sections. So making sure you understand the ins and outs. Last thing here is calculations I would expect you to be able to perform on the exam. All right. So since we only have 50 minutes, not going to be too much calculation intense, but things I would expect you to be able to do, you might consider this list. All right. So take a look at that study guide. That'll help you on your way. And I'm expecting you to know material through slide 8 of lecture 6. So we're nearing the end of lecture 5 right now. Probably get to slide 8 of lecture 6 on Thursday. Almost surely we will. Okay. Any questions on that? Anyone? Noonan. No, please mask over your face. All of you guys. All right. In person, mask over the face. Question. The breath document beginning of lecture on Thursday. So 4 o'clock for the breath document to my email inbox. Other questions? Lucas. So Lucas is asking, do we have to have the exam sent in by the 50-minute mark? The answer is no. I'm giving you to the end of the hour. So 50 minutes to do the exam, 10 minutes to take pictures and send it in. Justin. I don't care how it gets to me as long as it's legible and understandable. Okay. More information on the exam to come, future date. All right. All right. So no more questions. Let's get on with the material. So let's get rid of this guy. And let's sort of remind ourselves where we were. So last time we were talking about transformations. We kind of left off talking about transformations, specifically three-dimensional transformations. So last time we kind of talking about 3D transformations. Of stress, specifically. We kind of went through a whole like 2D example of how we transform vectors, and we're now going to do that and apply that sort of in a three-dimensional fashion. And we were doing this by considering two three-dimensional coordinate systems. So here you have kind of the standard coordinate system, which is like the 1, 2, 3 coordinate system, which might correspond to some material axes of interest. Let's say the one direction being a fiber direction and 2 and 3 sort of being across the fibers. And you might have some loading condition that's not necessarily aligned with that particular axis, and maybe it's some other coordinate system. It's not necessarily aligned in any way with 1, 2, 3, except it sort of shares an origin, which might be like X, Y, Z. We can sort of define some things about the first coordinate system relative to the second coordinate system, and that would be like the angles that each one of the individual arms of the coordinate systems makes with the original 1, 2, 3 coordinate system. So we might define, let's say, the angle between the x-axis and the 1-axis as theta 1x, the x-axis and the 2-axis as like theta 2x, and the x-axis and the 3-axis as, you guessed it, theta 3x. All right. We could do the same for the y-axis, theta 1y, 2y, 3y. Same thing for the z-axis. And so you could ultimately end up with, let's say, 9 angles that exist between each one of these coordinate axis arms. All right. So if you have stress state given in x, y, z coordinate system, you can transform to the 1, 2, 3 coordinate system with the following relationship, and that is sort of in shorthand, you might do this as sigma 1, 2, 3. That's where you're ending up. Is this transformation matrix T times sigma x, y, z. This is sort of like the shorthand notation. And if you wanted to sort of write this in like long-handed full form, this might be something like this. Two, three. Never make this big enough. Remember, this was like our contracted indicial notation. The 6x1 vector tells us the full stress state. Equal to, I'll just keep this as T for now, but understand that this is going to be a 6x6. And that might be related to the stress state that you have in some random coordinate XYZ coordinate system. Here. All right. Yes, the order is important. Question from the audience. Does the order of this vector matter? Yes, the order matters very much. Yes, so the order I have written here is correct. And in general is related correctly. All right. So the question is, well, what is this transformation T? Well, the transformation T in 3 dimensions is similar to sort of the transformation matrix that we talked about in 2 dimensions, where it has kind of like this cosine terms of all these various angles. And so that transformation T, matrix T, all right, hold on to your hats, okay? Here comes Alex Ramiar. I hope your hand is loose. So if we let the following variables be stand-ins for directional cosines. So let's say define directional cosines. As the following. We have M1, M2, M3. These are going to be the cosines of theta x1, theta x2, and theta x3. Okay, so these are cosines of the angles that exist between the x arm of the XYZ coordinate system and the 1, 2, 3 coordinate system. We have similar N1, N2, N3. You should kind of like be reminiscent for you of like statics when you talk about directional cosines of Mn and L, right? But here we're using Mn and P for some unknown reason. So this will be for the y-axis. And then lastly, we'll do P1, P2, P3. This will be cosine theta Z1, cosine theta Z2, and P3 is cosine theta Z3. Okay, we have directional cosines now. Now we can define our transformation matrix. You ready? Are you ready? I wouldn't be able to fit it on the page if I tried. Here you are. This is in the notes. I would say don't copy this down right now. There it is. Yikes town. So here you go. It's a 6x6. And this uses the directional cosines that we just kind of defined. Please don't write this on your paper. Okay, this is in your equation sheet and also in the slides for the class. All right, so just like make a note on your paper, see slides or equation sheet. Okay, your hand is gonna cramp up and fall off. All right, these are how the pros do it, Alex. This is how you maintain your hands. All right. So you get the general idea. So you can use directional cosines that exist between these two three-dimensional coordinate systems if you know the angles between the various coordinate systems to get you your transformation. All right. Then you can transform from one coordinate system to another in 3 dimensions, just like you might in 2 dimensions, which we kind of talked about on some of the previous slides. All right. Well, why is this a useful thing for us? I guess let's put the finishing touches on this. All right. So then you can use sigma 1, 2, 3 equals t z. If for some reason you want to go back the other direction, you can just take the inversion of this. So from 1, 2, 3 to x, y, z, you can use the inverse. We all passed linear algebra. Suspicious. Ah! All right. So this also applies. Where, remember, these are like 6 by 1. This is a 6 by 6, and this is a 6 by 1. I would not advise trying to calculate the inverse by hand. Oh my God, don't do that. Go to MATLAB or go to your calculator, calculate the inverse, using a computational tool. Oh my goodness, I couldn't even. Do you guys like ever have to do manual inverses in like your linear algebra class or like the Jacobian theory and stuff like that? Oh gosh, makes me want to throw up. All right. Yeah, don't do that for your homeworks. All right, please use like a computational program. All right. All right. So let us continue. Just like we did for stresses, we can similarly do the same for strains. All right. They'll say similar for strains. Except we have one little caveat here, and that there's kind of a factor of 2 that floats around. So if you remember from 3005, when you're talking about strain transformations and stress transformations, there's always like this pesky value of 2 that floats around. That's just because of the way that we define shear strain. Okay, so if you have like some, I'm just going to do this quick review. In that the way that you like define shear strain is if you have some, original configuration. Here. And then you have some deformed configuration. Call it here. The shear strain is more or less this angle here. This is your gamma x, y, if this is like an xy coordinate system. But notice here that we kind of have this angle twice in this particular configuration. So it also exists over here. And more technically, let's make this technically accurate. This is epsilon xy. This is written as epsilon xy by convention. So then what you would see in like your 3005 class, you'd have something like gamma xy is 2 epsilon xy. So this is actually half of the shear strain by definition. Right. that's sort of how we technically define. So what I mean is there's like this pesky factor of 2 that floats around just because of the way that shear strain gets defined. All right. And so because of that, the transformation matrices for transforming stress in the 1, 2, 3 coordinate system to the XYZ is different than the transformation matrix going for strain in 1, 2, 3 to XYZ or back and forth. Okay. So there are 2 different transformation matrices, one for transforming stress, one for transforming strain. And that's just generally because of this silly factor of 2 that floats around. So the general rule here is that gamma xy is 2 epsilon xy. Gamma xz is 2 times epsilon xz, and gamma yz is 2 times epsilon yz. And remember, we label these in our strain vector and contracted notation. This is gamma 6, this is gamma 5, and this is gamma 4. So hopefully we sort of remember that. So that when we sort of define the strain vector normally, let's say in the 1, 2, 3 coordinate system, this is epsilon 1, epsilon 2, epsilon 3, gamma 4, gamma 5, gamma 6. So remember, this is your contracted notation for strain in the 1, 2, 3 coordinate system. Kind of written out fully. Right. So transformation matrix. For epsilon x, y, z to the 1, 2, 3 coordinate system, slightly different. And kind of annoying. But the general idea here would be something like, and by nomenclature we call it T star. Right? And I like the T star is for strain, like the ST. It makes me feel better, even though ST also goes with stress, but don't tell anyone. Okay. So then we would write, if we wanted the strain in the 1, 2, 3, this is simply the strain transformation matrix T star multiplied by the strain in X, Y, Z. Remember, this is still 6 by 1. This is 6 by 6. This is 6 by 1. And I will not write it again, but I'll post it up here if you want to sort of take a look. There's your T star matrix. Also in the notes for the class. And if you're watching this on YouTube, which, you know, maybe some of you are later, you can pause this and write this down if you really want to. Okay. Again, using those same sort of directional cosines. All right. Same idea is true for using the inversion. If you want the strain in the X, Y, Z coordinate system, you can use the inversion. And the last little interesting bit of information, which I always thought was kind of tricky. These are related through the following information. The T star inverse is equal to the transpose of T. Who would have thought? So if you're working in MATLAB and you like punch everything in for T and you want to get to T star quickly, you can transpose T and take the inverse, and there you go. You got T star. Booyah. Okay. Almost done with our math precursors. I know it's been kind of a mathy sort of week, but hopefully you guys like that. You know, engineers, we like math. Remember, we started this whole debacle in this whole conversation with like Hooke's law and these like compliance and stiffness matrices, right? So what we ultimately want to do is not like transform stresses and strains. We want to transform stiffness constants from, let's say, an XYZ coordinate system to a 1, 2, 3 coordinate system, or vice versa, right? So now if we want to sort of enact that sort of transformation, we can do that using known information about the transformations of stresses and strains to transform appropriately. So let's look at a transformation of a stiffness matrix. All right. So let's start by basically writing Hooke's law in a 1, 2, 3 coordinate system. And that is the stress in the 1, 2, 3 coordinate system is the stiffness matrix C in the 1, 2, 3 coordinate system multiplied by the strain in the 1, 2, 3 coordinate system. Hopefully that's easy to understand. If we just have like this one coordinate system, we'll just write Hooke's law in that one system. All right. But now let's say that we actually have some stress state in XYZ. And that's really what was going to be important for us here. So let's let our stress in the 1, 2, 3 be written in terms of some stress state that we might have in XYZ. And we know that we can do that through the transformation matrix T. Right. Similarly, we could do that for the strain as well. Except now we use T star. Okay. So we can begin to make some substitutions. If we call this equation up here star, we can sort of like substitute these guys into star. And you'll end up with the left-hand side replacing sigma 1, 2, 3, right-hand side replacing epsilon 1, 2, 3 with their associated transformations. So here we have like transformation matrix T times the stress X, Y, Z equals still our compliance matrix in 1, 2, 3 multiplied by the strain transformation matrix T star. Here I'm replacing epsilon 1, 2, 3 with T star epsilon X, Y, Z. You know, we multiply both sides by T inverse, specifically the left-hand side of both sides. Remember, when we're doing like matrix multiplication, we have to be very careful about multiplying, you know, where our matrices are multiplied. All right, well, if I multiply T inverse by T, that's just going to be the identity matrix. I can sort of just drop that off. So I'll end up with the left-hand side here. That's just the stress in the X, Y, Z coordinate system equals, I multiply the left-hand side here by T inverse times C, 1, 2, 3, times my strain transformation times the strain in X, Z. What we notice here is that sort of on accident, okay, I didn't do this on accident. We have stumbled upon Hooke's law in the XYZ coordinate system, okay? So we notice here's the stress in XYZ, here's the strain in XYZ. So this here must be the stiffness matrix in XYZ. Okay. So we notice here then that if we want like compliance matrix in X, Y, Z, then this is T inverse times stiffness matrix in 1, 2, 3 multiplied by T star. I have a comment. Accidentally on purpose. Exactly. I accidentally on purpose stumbled upon this Hooke's law in the XYZ coordinate system. So this is kind of the conclusion from this particular portion, is that if you know the stiffness matrix in the 1, 2, 3 coordinate system, you can transform to the XYZ coordinate system using these transformation matrices. Right? There's also sort of the inverse of this. Which is if I want the stiffness matrix in 1, 2, 3, and I have it in XYZ, it's a little slightly different, but the idea is more or less the same. These are yeah, sorry, thank you. Next. Could do similar. For the compliance matrices. Which remember is like S, which is this remember that's your inverse of the stiffness matrix. This is the compliance matrix. It's capital S. Yes, the compliance matrix is S. 0 cents. 0 cents. Doesn't make any sense. Where if you had X, Y, Z, this could be written as T star inverse times the compliance matrix that you might have in 1, 2, 3 multiplied by the transformation matrix T. Or the other way, yours is going to be T star multiplied by compliance matrix in X, Y, Z multiplied by the inverse of T. Okay, so here we are. Now we have tools. We have tools that we talked about over the last 2 weeks that are tools like what is the modulus in the 1 direction, in the 2 direction, and the 3 direction using micromechanical models, right? HALP and psi, exactly, for instance. We can use those calculations to populate like the stiffness and the compliance matrix in a material coordinate system 1, 2, 3. You can populate C1, 2, 3, you can populate S1, 2, 3 using micromechanical models and information of like E1, E2, E3, nu 1, 2, blah, 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 we've already talked about. And now if I want, what are the stiffness properties in an axis that is not necessarily aligned with 1, 2, 3, maybe some XYZ arbitrary like loading coordinate system, you can do that if you know the angles between your arbitrary XYZ coordinate system and maybe the material coordinate system 1, 2, 3. All right. So hopefully we see the power now of these transformations and how they can be useful in defining material properties off axis. All right. So let's put a bow on this and we'll call it for today. This is going to kind of conclude this like mathy portion that we sort of had to walk our way through, okay? For materials that obey conservation of angular momentum, remember that gives us this general relationship. And are Cauchy elastic? Remember that is this general relationship. That your stiffness matrix is symmetrical. We require 21 independent material constants to fully define behavior. Okay. We saw that isotropic materials only require 2 constants to fully define. The Cij, right? We wrote it in terms of lambda and G, You can kind of go back through the notes and take a look at that. But could also be written in terms of, take your pick. Elastic modulus E, Poisson's ratio nu, bulk modulus K, Lemay parameter mu, which I didn't even talk about. That's the second Lemay parameter. Okay, only require 2 constants. So you can reduce this like 21 independent constants required to define a fully arbitrary sort of generic anisotropic material down to 2 by leveraging symmetry, which we haven't talked about yet, but we'll talk about over the next few lectures. So 2, simplify Cij from 21 independent values like for a general anisotropic material to 2 is like isotropic. We need to leverage symmetry inside of the material. I'll say we'll need to leverage the math behind planes of symmetry and planes of isotropy. And this is what we will do next week. Well, next week, I'll say next lecture, because we're going to do it on Thursday. All right. That's it for today. We'll break, work on a manufacturing document, due on Thursday. See you then.